Hello, my name is Jessica. I'm joined by my teammates Gugu and Mklengi, and we're here to discuss unlocking salinity markets in Southern Africa through halophyte cultivation and desalination. So many of you have all heard about climate change and how it is leading to fluctuations in global temperatures. This means that we are getting extreme heat and cold. But something that is not as discussed is that climate change is also increasing salinity. And this happens when things like sea levels rise, the ocean water infiltrates freshwater systems and contaminates groundwater with saline. The increasing temperatures also increase evaporation and alter rainfall, both of which increases the salinity found in soil and water. Now, this increase in salinity negatively impacts on food production as most crop plants aren't able to tolerate high salt. And this moves us away from achieving the United Nations Sustainable Development Goals of zero hunger, clean water and sanitation, life below water, and life on land. So it's a big problem. Now, specifically, when we look at agriculture, this excess salt just this excess salt disrupts photosynthesis as plants aren't able to absorb water as it goes against osmosis. And without water, plants obviously aren't able to grow, which is resulting in reduced crops. Now, to compensate, farmers, of course, can just water their plants more frequently, but this uses excess water, and in a water-scarce country like South Africa, it's not a sustainable solution. So something else has to be done. High salinity is also resulting in farmland being abandoned, as it's simply not able to grow crops there. And again, in South Africa, only half of our land is able to be used for farming. So if we're losing farming land, it contributes to food insecurity. And this all results basically in how salinity is contributing to major financial and socio-economic losses.
Various technologies have been developed to desalinate or remove salt from water. One of these is a multi-stage flash, which actually utilizes high heat to remove salt from sea as well as brackish water. This involves using high thermal and electrical energy in the heating process and allowing and therefore after this process capturing the evaporation, cooling it and capturing the less saline water. However, the system also produces high brine levels, which is a concentrate of salt, and this also further challenges the removal of this high concentrated salts and its management. Another system is a multi-effect desalination approach. It is better at recovering more water or desalinated water compared to the previous approach through its ability to utilize steam instead of direct heat. However, the challenge of brine is still evident in this system as well, complicating the management of this highly concentrated medium. Alternatively, we have the most efficient desalinating approach amongst these conventional approaches, which is electrodialysis, able to produce up to 90% of clean water or recover up to 90% of clean water. This approach makes the use of electrodes where positive ions would be attracted to the negative ion cathode rather, and um, and negative ions within the saline water would be attracted to the anode. This leaves room to actually attract pure water from the center of the system and have higher quality to out throughput. However, these solutions are really cost intensive, particularly in setting up industries that are able to do this at scale, but also the need for high thermal and electrical energy also um, except also increases the cost of the system, making it inaccessible at a local and farmer level. So there have been work to actually test out new or alternative approaches to these conventional technologies, and these have been utilizing a nature-based approach. For instance, we have microbial desalination cells and biomembranes, which utilize microbes that are able to survive and utilize salinity within their metabolism. These approaches are still, however, in a lab setup and haven't been demonstrated at scale compared to the conventional approaches, despite their relatively high recovery rate of desalinated water. As an alternative to this, or additional to this, there's halophyte use within this nature-based context, which utilizes plants in actually capturing salinity from the system. Little work is available, though, on actually capturing how much recovery from the system is possible, considering halophytes are usually grown in natural environments where the water itself is not recaptured directly or on site. So this means that halophytes have been utilized in reconstructed wetlands where there has been a need to clean out contamination from adjacent industries. Also, a limitation might be the extended production period that would lead to changes in water quality, desired changes in water quality.
A commonly cultivated halophyte is an example of quinoa, which is better described as a facultative halophyte, meaning that it can tolerate salt but generally prefers low salt conditions. However, in Southern Africa, there's quite a range of naturally occurring extreme halophytes that actually require salinity for growth and development. And examples of these include saliconia and tetragonia. So these plants, they really thrive in salty environments, and through their specialized physiological adaptation, such as salt exclusion, salt accumulation, and antioxidant production. Whilst it is quite important to leverage these properties to develop a halophyte-assisted system that can lower desalination cost while also helping local communities and farmers to access desalinated water. In addition to just getting desalinated water, halophytes can also provide food sources, and it also enable nutrient and mineral recovery from saline water, and also produce biomass for biofuel and other industrial applications.
Our current work has been looking into developing seed-independent protocols to produce these halophytes at scale. Current work has been successful as far as developing seedlings, particularly of a southern African halophyte called Saliconia pilansi. We've also been able to demonstrate um, the applicability of these species within saline aquaponics environment. For instance, in this picture, we are able to see salt crystals forming within the process, demonstrating a combined effort between siliconia as well as substrate choice in improving desalination or water quality over time. So this really, as part of our startup mission, we are looking to actually leverage on the siliconia cultivar, cultivar and species to develop our very first cultivar for siliconia that can be applied in both food production and resource reclamation contexts. This is part of our mission to unlock salinity resilience and markets, particularly at a local and farmer level, and letting these resources being utilized at that level. This would actually allow us to use siliconia as both a food and food additive, either as a vegetable or salt substitute, but also support environmental management practices within an aquaponics system, as well as other environmentally stressed industries. We anticipate that we'll be able to source saline water and support industries in aquaculture, saline water, groundwater stressed environments, which is also a pain point for most of our farmers, but also support conventional desalination approaches by making use of brine, which is produced within their systems. We will be able to utilize these leveraging infrastructure that is already in use in most of our local production regions with our ability to produce food, biomass, and desalinated water at a local level. We'd like to acknowledge these institutions and individuals for their support in our work. Thank you.